So before we broke, last time I forgot to ask questions and everything. Thought I'd give a chance here. Any questions before we jump into disinfection?
You're getting off easy.
I am. Well, and I'll be, have a session after this for questions, and then I'll be around afterwards in the hall. So,
Then tomorrow morning, what time do we start?
7 a.m.
Okay.
It's always tough at the National. So coliform control and disinfection. In the States, it came on pretty strong. First coliform rule was in '97, and it's been revised 4 times since then. But at first, it caused a lot of disinfection and a lot of closure of well systems that could have been saved just from the application of the law, the application of disinfection. Since that time, and most current reauthorization was 2017, it's become a lot more of a palatable and more effective rule. And just from what I could tell, the Canadian regulations, you reached that a little bit earlier than we did, maybe a little slower down south there, oxygen or something. But I'm going to talk about some of the reasons we've seen failures, some of the things we advocate, and at the end I wrap up with my 12-step protocol. And it can be applied both in screen wells as well as open completion wells or open bedrock well systems. There is going to be some repetition, especially when I talk about some of the testing compared to what I talked about earlier today. I apologize for that, but there are important things to get across, so bear with me there. So coliforms, we use them as an indicator. And the reason they work so well is because that class of bacteria is very broad, and it does include the whole gambit of the enteric bacteria, those that are related with fecal. But as we get to that broad class of organisms, it also includes a lot of soil bacteria. Soil bacteria that naturally show up as part of recharge and within the environment of our well systems. So, that's a big difference to understand both for our regulators to understand, but for the well owners and for ourselves. So, while that test is a good indicator, it should not be used as the kiss of death for a well system. As I mentioned earlier, it's a very easy test. It doesn't take a lot of training and run up to operate it in the lab system. It's not as sensitive as labs will allude to. You do actually have some flexibility on timing, but it's a very effective, very cheap. The core test itself costs about $5 US there to run, and you can run a number of them. In Canada, the MAC is non-detectable per 100 milliliters. Stateside, it's per 10 milliliters. So there's a good differentiation there when you're working with a lab. Different levels will trigger different responses. So stateside, you get a coliform hit, you need to retest. If it becomes kind of a periodic issue in the well system, you're going to explore the system, look at vulnerabilities. And one of the big changes I've seen on both sides of the border there, one is separating the E. coli test out. Very good, those are specifics to enteric contamination. But then also coming up with treatment plans for the well system. Even if you don't need them at that time, have a plan in place for the next time that the coliforms present themselves. So one of my favorite images, to tell you what you're looking at. This would be the Garden of Eden with regards to bacteria. It was very vibrant with visual activity. In the slide, I'm very hesitant to show videos because depending on what computer I'm working at, I have a break apart there. So it's a freeze frame, but we had Paramecium, Spirillum, Vegetoa, so a whole mix of larger microorganisms that are indicative of surface activity. The Vegetoa is a sulfur oxidizer that forms a thick mat of biomass, much like oatmeal. But this was a coliform-free sample, so it had a negative test results, nothing present, and was actively being used as a potable water treatment source. So some general information about coliforms. They typically are anaerobic or facultative anaerobic bacteria. So while we catch them in the grab sample from around the pump, more often they're in the lower extension of the well system. where either flow has been impacted because of fouling or is reduced. It's not uncommon, especially in deeper well systems, to dig the well and try and maximize production. And maybe that well, that lower extension is hydrologically isolated, might contribute 3 to 5%. And that's a perfect place for these anaerobic bacteria, including coliforms, to reside. What we have found, both research in our lab and across the water industry, is as a bacterial population matures and the biofilm grows, it's more likely to harbor coliform bacteria. Now here's an example on the occurrence of anaerobic growth and the rate of occurrence of coliforms that we looked at before. So with that increased biomass and increased biodiversity, higher levels of anaerobic growth, more dense biomass that keeps the oxygen out, we're more likely to see environmental coliforms develop or harbor in that portion of the well system. The heavier anaerobic growth is less likely to be flushed out during active use of the well, and it's likely to incorporate other fouling mechanisms, precipitating mineral scales or sediment that come into to migrate into the well system. And so that can increase the nature of the fouling that we have to deal with and degrades the potential effectiveness of simple chlorination. So kind of what I touched on. Once we know the occurrence and what's going on within that community, then we can target our problem. And more often than not, we catch a sample during cycling of the well up at the pump. It's, you know, we catch it, we get a positive hit, and really the problem is down in that lower extension. And if we just try to cycle the pump, we may flush that area around the producing zone, but we may not fully address that lower extension. And if we try and dump chlorine or another oxidative compound from the surface, or cycle it through the pump, again, we may just target that area that we caught the sample at, and really may not get to the root of the problem. So when I have a customer come to me, they had a coliform hit, and unfortunately, usually they've had multiple by the time they come to me. So they'll ask me, you know, what do I do? The first I'm going to ask them is to classify the organism, and that gives me a better idea of where it is and where it's from. Did it naturally develop within that environment downhole, or do we have an indicator of, let's say, root traces, or active soil bacteria, or vegetative matter that's going to give me some insight there. Also, I can rule out fecal coliforms at that point. Also, enumerate, so get a population count of the coliform. As an example, if we get environmental coliforms developing naturally downhole, they could be 2 to 20 per 100 milliliters. And that's big. It's still going to trip your test. But a true septic system influencing the well system is going to be 2,000 colonies per 100 mils. It's going to be several orders of magnitude more. Flooding, when you get a little bit of everything from a river system introduced, that could be around 200. So that still is a problem we've got to address, but it's not the level of direct contamination. It's something we can actually deal with. After we enumerate the coliform issue, let's get an idea of the bacterial community in general. How large is it? Is there more biofouling issues going on downhole? And then, as always, anytime, let's investigate the well and the well site. So for testing, identifying the community. One of the easiest methods to do, one of the most common, and it dates back to the late 1800s, is the heterotrophic plate count. Depending on the test and the methodology, it's going to give you a range of 0 to 500, 0 to 1,500, or 0 to 5,000 colony forming units. And your heterotrophs are predominantly aerobic bacteria. While this has been a really good method and it is an industry standard, it's very dated. What we have learned now in the microbiology world is that roughly less than 10% of the known groundwater bacteria grow on heterotrophic plate. But if nothing else, it will give you an assessment of the reactivity of the bacteria. So if that's the best you can do with your local lab, it's some information is better than none. ATP, the adenosine triphosphate, is a relatively new method. It came from the food industry as well as the dentistry side of things. And it gives us a flash count, of total bacterial population, aerobic and anaerobic, all living bacteria. You're small, you're large, regardless of if they would respond to a blood auger or not. So some of the ranges on a standard 0 to 1,500 HPC, once we get above 300 colony forming units, we have the potential for dynamic colony growth. Certainly the higher we get in that level, the greater potential. On ATP, which is cells per milliliter, a typical well system will have between 1,000 and 30,000 cells per milliliter normal. That's your background resident population within the aquifer. As a well fouls, it pushes closer to 100,000, and as we have the potential for heavier anaerobic growth in coliform, that population typically increases to 500,000, especially with regards to biofouling. As I mentioned, ID the coliform, look at the rate of occurrence. Understand the maturity of the population in general. Look at our anaerobic levels. And this might be, if you only have one test to go to this. Because the more anaerobic growth we have downhole, the more impeded flow we have, and the more likely we're going to be able to isolate where our problem is, the lower portion. The results are given in percentage of the total bacteria, and so it would be the total that are anoxic, or like the lower extension, more dynamic biomass to get the oxygen out, more of your opportunistic pathogens, your sulfate reducers, and other nuisance bacteria fall under this category. So what I would look at is, if you've got a coliform issue and you can only run one test, run the anaerobic growth level. If you've got greater than 20%, we typically have a cleaning problem as opposed to a disinfection issue. That well just needs some TLC. And that's not uncommon, especially in residential wells where preventative and regular maintenance is more of an afterthought. Look at how the well has been utilized. One of the big challenges we get is from real estate agents that will call and they're dealing with a property and it keeps hitting coliforms. And so I'll ask them, well, how long has this house sat vacant? Has it been off the market? Did someone in the family die and it's got to go through probate? And they always wonder, how did I know that? Who have I been talking to? Well, it's this common issue that we found when a well system, especially for a resident, is sitting offline 6 to 8 months. When previous to that, it was used every day for years on end. When it goes idle, the problems develop. All the sins of not taking care of it, or any failure in construction or influence on it, multiply as it sits idle. So, if nothing else, you run the anaerobic test, and while you're waiting for those results to come back, pump the well. Let's flush it. Put a little stress on it. Try and get anything that's stagnated and built up into it, flush it out of the well system. And it's a little washed out, but you see this, it looks like mud in the pit here. It's not mud. I'll let you use your imagination there. Investigate the wellhead. There are always these surprises. You know, did the well get hit by a lawnmower? Did someone back into it? Was there a storm event that eroded around the well surface? Did a sanitary sewer back up into the vault there? Oddly enough, it wasn't tripping coliform issues, just environmental coliform. But that's always an easy one. And then move back from the wellhead. What's happened in the area around the well? And with residential wells, you're talking about a 100-foot radius. In larger well systems, you want to look a little bit further there. Areas of recharge, of runoff, changes to the use. Has industry moved on? What was once pasture is now acres and acres of homes. So look at the changes there that could have influenced the recharge and the water or the products going into that well system. This is one where they had routine failures, and it might be a little washed out, but what we have here is you can see they've got what they call a crow's nest and an elevated ladder because this area does get flooded. Now, it had received some pretty substantial flood waters in the last 8 months ahead of this, to the point that the pad for the ladder there is completely gone, and the animal that had taken up residence around the well seal there had been drowned. So you've got vulnerabilities here, you've got vulnerabilities of the whole structure. There's corrosion occurring on the crow's nest, the anchor point here, so we know that the area was destabilized. A simple dye test let us know that there was direct conduits from the surface into this well system. When we investigated further, and up in here is an active farm field, we found a lot of nutrients. Nitrates were very high, a lot of beautiful topsoil in the bottom of that well system. As I mentioned, more often than not, The coliform occurrence is just the final symptom of a problem, poor maintenance. And this is true for wells of all sizes. You know, as much as we advocate not doing it, we're an industry where our customers run to failure. And so, you know, we'll get away with a number of years just doing simple disinfection, and then disinfection no longer works. And we look a little closer and we have problems like this. You know, the biomass is so dynamic here, it looks like melted candle wax. And this is the producing zone. You know, so there's very little flow that's getting through there, and what flow is a high bacterial load on it. If we've got to clean the well, let's use multiple methods. Let's go in first mechanical, flush out the lower extension of that well, knock all the debris off, whether it's mineral or biological or a combination, get that material out. Even if we just go back in with simple disinfection, it's going to have a greater potential to getting into the nooks and crannies where our problem bacteria are hiding. If it's, depending on the system, if we can pull the pump, let's pull the pump, power wash the column pipe, disassemble the pump if it's a larger system. If not, look at the need for replacement. Try and clean and disinfect that equipment as best as possible. I also strongly advocate when you pull this material out of the well, regardless of the well size, keep it elevated. If you've got to put it on the ground, put it on plastic. And it's just CYA. Let's give the best potential to remove these problems and not reintroduce anything there. Age old, and what we have is state extension offices, and they handle with a lot of the rural, a lot of the ag well systems. And they will still, in many states, advocate shock chlorination. Shock chlorination is using a high concentration of chlorine, typically around 1,000 parts per million, to alleviate the problem. It's a nuclear option. And how we got to it was chlorine is cheap, a little is good, a lot's got to be better. And I was victim to this myself. You know, I don't want to use the rest of the jug. It says I only need a cap full. I don't need this at home. Let's just empty it all in there. You know, when we're pushing 3,000 to 4,000 parts per million. And what happens is we over-oxidize the biomass. And so we've got free-swimming bacteria and the water flow going over the puffy paleo biomass that looks a lot like this in a well system. We hit it with this high oxidative chlorine concentration, 1,000 parts per million. We'll cook that polysaccharide. We'll cook that into a very effective sugar. You know, what will happen in short term is that biomass will recoil like a snake. And it'll pull back. You'll get some improved flow. And you can get some kill with the free-swimming coliforms, but anything that's hiding under there, it's now got a food source. It doesn't have to send out for groceries. And so you will see in very short order an explosion of population. And so you do get some temporary relief from the problem, but in long term, it's been very detrimental. And we've got a much more dynamic bacterial community to target. What we have here is we've got a screen zone and just beautiful slime-forming bacteria. I guess the kind of nerdy to say that, but it's all the dynamic buildup of this polysaccharide slime. What was challenging here is this well was less than 6 months old. Completed the wells, developed them out, so they knew they had good flow, got all the fluids out, all the cuttings, all the disturbed material, and then pulled everything and waited for infrastructure and the pump to get in. Put the pump in, turned it on, immediately seized up, and it was just large accumulations of biomass. Even upwards flow without a pump. And so you see the biomass kind of trending in that direction. That's the material that hides. And if we shock chlorinated that, it would recess, but then it would pounce back and with aggravation. So very similar slide to what we talked about earlier, but targeting disinfection. What we advocate is between 50 and 350 parts per million. Do not go above 500 or you risk being overly oxidative depending on your water chemistry. At 50 parts per million, you have sufficient to kill your bacteria, you get the biocidal effects. If you've got a lot of iron or manganese or other products that within the water quality, the water chemistry that will neutralize or reduce the effectiveness of that chlorine, bump it up a little bit. So if I've got a lot of iron in my formation, or I've got a very corroded well screen or well casing, I typically will push 300 to 350 parts per million. is that iron will consume some of the chlorine, and I'm accounting for that, but I've still got enough chlorine to get the kill that I need there. Chlorine is very reactive with other chemistry, like we talked about. It can be very dangerous. You can have off-gassing and death. At times, we have to look at pH adjustment. And what we're trying to do there is to undo that buffering that they do for safety. So if you remember when I talked about the sodium hypochlorite being buffered to a 9 to 10, depending on the product, at that point, your biocidal effectiveness is about 2 to 3%, 4% maximum, depending on the strength. But if we lower that to a 6.5 to 7.25, we increase the 96% effectiveness on the biocidal activity. Do we have to use a special acid? We do not. But we have to be very ginger, very light-handed on the acid addition. I would say buffer your core water to about 5.5 before you add in chlorine. So we're outside the off-gassing range of 4. We're in a safe area there, but we're still in an efficient zone to generate the hypochlorous acid or the biocidal agent.
So how are you calculating your parts per million on the water in the column or in the?
Great question. And I'll just go ahead and address that. So another thing that we advocate is think outside the column. So, where can we exactly? And it's gonna, you've got to be within reason, but upwards of 4 times your standing water column of water. So I will calculate, let's say 3 to 4 volumes, depending on the size of the well, at the surface. I'll buffer my pH, I'll add in my chlorine concentration, let's say we're targeting 200 parts per million, and then add it into the well. You will have a little bit of dilution, but injecting that, you're going to get volumetric displacement. And you're still going to have a viable chlorine concentration within that borehole and hopefully out into the aquifer formation interface zone there.
So you're going to recycle it, or how are you going to?
Good question. Ideally, I'm going to drop a surge block in there and get some activity. You don't always have that luxury. If I can do pump-to-tank surging and pump from the well into the mixed tank and then back and forth, that gives good volumetric displacement with some agitation. That's better than nothing. But kind of like with the cleaning before, the mechanical activity is really good. And it's even more important for physically dispersing that solution out into those nooks and crannies, those hard-to-reach areas that we just can't get from dropping it at the surface. Great questions. We talked about this a little earlier, the 3 main kinds of chlorine that are available. Sodium hypochlorite is going to be the most common. It's a liquid form, it's relatively easy to get, very, very convenient there. It does degrade, so keep that in mind. If we've got an ongoing customer or an ongoing challenge, I would go to the extremes to make sure you're dealing with a fresh, active form. The best way to do it, you can uncap it, you can smell it, and you can take a total or free chlorine test strip and check it right there to make sure that it's still viable. It's generally going to be buffered for safety, so when we're using sodium hypochlorite, unless our core pH is already in the 5s in the groundwater, which it does occur in some regions throughout the continent there, unless it's that low, we're generally going to have to buffer it with an acid. And if we've got a very stubborn, very tight formation, or a very deep setting, we may want to add a surfactant to that. With calcium hypochlorite, we want to put that into solution, whether it's powder or pellet form. We want to use generally a little bit of warm water, something above 56 degrees Fahrenheit, mix that, get that into solution before we add it into the well. We may also need to buffer the pH too. And if we do have a calcium issue, we know that we've got hard water above 18 grams, above 180 parts per million. We want to go ahead and adjust the pH there a little bit so we reduce the potential there for scale buildup. The chlorinated isocyanurates, if you're familiar with Steriline or UL 420, this goes right into solution. It doesn't contribute calcium. It's very shelf stable. Very effective means of chlorination. We don't have to adjust the pH, so we're generating hypochlorous acid as soon as we put that into solution. This is the chart that I wanted to present to you earlier, and if you're looking for one, this is one I recommend. This has got all the chlorinated types, including the isocyanurates, in calculating per volume of water and desired chlorine concentration. Again, For disinfection, I want to stay between 50 and 350 parts per million. If I've got development, or if I've got a municipal system that may have had a backflow issue and treated water where the polymer got into the well system, then I want to push to 1,200 or 1,500 parts per million. But on a disinfection sense, I want to be in that lower range there. So to improve disinfection, we want to control the pH, we want to flood the well with a larger volume, we want to give it sufficient contact time, I'll talk about that in a minute, and then we want to monitor the reactions. And I apologize, I got my slides mixed around here. So this is the pH chart that we talked about. And the hypochlorite ion is our safe, transportable, stable ion that our sodium and our calcium hypochlorite come into. Hypochlorous acid is the disinfectant agent. That's where we get our biocide. And when it's in acid form, we're in that 4.5 and lower, it's at 100%. It's a very, very effective biocidal agent. As I mentioned, can cause fatalities. And that 6.5 to 7.25, we're in that 80 to 90% range there of hypochlorous acid production. Much more effective. Doesn't take a lot, depending on your alkalinity. If you're less than 200 parts per million, maybe a gallon per 1,000 gallons of a weak acid. So a little goes a long way there. Chlorine enhancers we talked about earlier, designed to adjust the pH for you. Some of them are surfactant based, so it increases the penetration of a filter pack. Some of them also have secondary cleaning, so you don't have to go through the full cleaning process unless the well is really heavily befouled. With the total coliform failures that we had in the early 2000s, the Michigan DEQ, and they sit with the Upper Peninsula and the Lower Peninsula right on the Great Lakes. And there's a ton of shallow alluvial wells, drive point wells. I heard something like 8 million wells within that state. A lot of temporary use, cabins and cottages on the lake or in the wooded areas of the Upper Peninsula only see 3 or 4 weekends a year use. And so they were having a lot of coliform challenges. And they did a deep dive and a ton of research on what was the best contact time for chlorine. And so they came with a minimum of 1,000 contact units. And the 1,000 contact units is the end result of the chlorine concentration times the hours of contact. So if you're using 200 parts per million sodium hypochlorite or isocyanurate or calcium, how do you get to 1,000? You take that times 5 hours to get your 1,000 contact units. This would be the minimum. I'm always a strong advocate, especially if it's been a problematic well system. Push it to 24 hours if possible, as long as that chlorine residual is stable. Now, over 24 hours, I wouldn't advise it. You have the potential for corrosion, and if the problem is that stubborn, you generally have got some cleaning to do. But at least 1,000 contact units or maximum 24 hours. Monitor the reaction, and I just keep saying this over and over again, regardless of what procedure we're doing, but very true on coliforms and disinfection. Confirm that the chlorine is viable. The product you're using, the mix that you made, and once you've added it downhole. These test strips you can get through Amazon, through a number of online retailers there. Look for your total chlorine, and you can get as accurate or as wide-ranging as you need. Very easy to use. I think a test canister of 50 runs about $9. So really easy. Just make sure that it's still viable. They've got about 18 months of
This is the chlorine one.
This is the chlorine one. ITS for International Test Strips is the company that we've run through the lab and checked the bases. So when we go out to the field, we always use their test strips, but they're available through Amazon and other retailers. Type in chlorine, don't just type in test strip. The results are quite a bit different. Really? Kills in Kansas. Once you've chlorinated, keep the well active. Again, this goes back to wells that were sitting idle, but once we've gone through that effort, even if it's just a low turnover or a low pump to waste or just a couple hours during the day, while you're waiting for the test results, keep it active, keep flushing it, keep a good turnover. On the neutralization side, we talked about this a little earlier there. Depending upon your local regulations, you may need to be below 1 part per million. So products like the New Well 500 or Chlor Out or sodium disulfate or sodium bisulfate will rapidly neutralize the chlorine. A little goes a long way. Very difficult to over-treat that and create a secondary problem like we could with the acids and the caustics used. Generally, that goes right in the solution. So the other thing is if you don't have those chemistries available, open air tank in the sunshine. That may take a day or two to neutralize that chlorine and settle out the solids, but it can occur naturally. My protocol, and this is typically for screened well systems, and just kind of walking through some of the slides that we visited today. We're going to identify the problem. We're going to, and that would be the nature of it. Is it a fecal coliform? Is it environmental coliform? Is the well fouled and not had any cleaning? We're going to investigate the well, and if nothing else, we're going to pump the well. Multiple volumes, make sure that we don't have any stagnation going on. If we're going to proceed with cleaning or a more involved disinfection effort, let's pull the pump, brush or clean as a preventative, or a pre-treatment, and then fully evacuate. If it's heavier than that, if it's more advanced fouling that our testing showed, then we'll proceed with the cleaning at that time. Evacuate all debris. Even if we don't do the pre-treatment of brushing, let's get down to the lower extension of that well and flush out anything that may have built up there that could be harboring the coliform bacteria or is also going to consume the chlorine that we utilize. Prepare our chlorine solution, 3 to 4 volumes. Even on larger wells where this may create 20 to 30,000 gallons of treatment solution, I advocate this flooding to completely disperse that solution throughout the entire column. Confirm that our chlorine concentration is viable, whether that's checking the pH or checking the mix ratio or both. Confirm that that solution is active and is at our target goal before we add it into the well system. If possible, try to trim it throughout the perforator or the producing zones. If not, trim it directly to the basement of the well and just keep adding until we volumetrically displace. Provide any type of agitation possible. The mechanical energy will help the physical dispersion, and if there is any cleaning that needs to be done, it's going to provide some secondary benefits there. Let the solution achieve its sufficient contact time, however we need to reach that 1,000 contact units. And if at all possible, let's leave it down whole overnight, 12 to 24 hours. When we're finished, pump the solution out. If we get to about 50 parts per million, go ahead and set the permanent pump and column pipe. Once we've power washed and cleaned them, set them into the well system, and then go ahead and evacuate the rest of the material out. While we're waiting for results, we'll go ahead and sample and submit those to the lab for evaluation. And while we're waiting, we're going to go ahead and keep the well active. With open borehole, very simple methodology. The one challenge is your mechanical going to be a little different there. In that respect, I don't recommend a surge block or a brush. Low pressure jetting is very useful. Airlift and adductor pipe is also useful. We still want to flood the entire area there, try to account for the fracture system, and you're going to know better than I what that will mean. Maybe we need to look at 5 times the volume, or maybe we're going in at 2 to 3 because it's a slower, smaller, tighter fracture system. And that's our disinfection discussion. Again, like I said, I rushed through the last one and got us to the break there and missed on questions, but are there any questions on disinfection and chlorination?
This sounds real simple, maybe, when you just dug wells. When you're treating with the JX12, like the bleach, treating a 21-foot deep well, 3-foot volume, 3-foot around, gives you roughly 900 to 1,000 gallons in a 21-foot section. How many would you put in? Half a gallon? Would you put a gallon? What would you put to bring it to your optimum disinfection?
Okay, so when you're dealing with right around 1,000 gallons, assuming we've got, let's say 180 parts per million total alkalinity, pH is neutral, I'd be looking at about a half gallon of an acid, a weak acid. And I would add it in, like, a quarter of that material, check my pH, add in a little bit more, and try and keep it in that 6.5, 6.75 range before I added in the chlorine. The other thing is as I added in that weak acid, I want to make sure that it's mixing, that I'm not just acidifying one part of the tank. Then I would add in my chlorine, certainly not going to stand over it, but open air, add it in, mix it again, and check both my pH and my chlorine solution. We should be right around a 7 at that range, and then we can proceed with our addition. With 1,000 gallons, let's say we were using 200 parts per million, the chlorinated isocyanurate, the 420 there, I'd use about a pound of it to achieve that 200 part per million. Now, if I had a lot of iron or a lot of manganese, or the TOC, the total organic carbon for that area is 2 parts per million naturally, I'm going to bump that up to 300 parts per million. So 1.5 pounds per 1,000 gallons. And my goal there is to allow some of it to be consumed by those other components, but still have enough for my biocidal activity. Good question. Others. One thing I will say, and you've probably all been through this if you've worked in the industry, when you're collecting a sample for regulatory purposes, flush the tap, flame it if necessary, rinse the bottle out at the sample port, then collect your sample. Wear your gloves, don't breathe on it. In the lab, we do know if somebody has staph infection or if they've got influenza. There are ways that you can contaminate a sample that have nothing to do with the well. Don't catch it on a windy day. These are just, like I said, if you've been in the industry, you know this, but from a laboratory standpoint, we've seen it all. It's kind of sometimes surprising. We got a sample in for confirming coliform presence, and it was a Mountain Dew bottle with duct tape written over it that said well sample, and it came from a UPS outlet. So we didn't even know whose it was to begin with, but we did know they were going to be out sick for the next week. Like I said, reach out to the labs. They love to talk to people outside of the lab. They like to share their knowledge, things that we geek out with real world people. And if we can help guide you on that, we're more than happy to. Yes, sir.
Did you say to rinse the bottle when you sample?
Yes, depending on.
Are you talking about chemistry? Because bacteria, most of our bottles come with sodium thiosulfate preservative.
Already within it? Okay. In that case, yeah, if you've got the reagent or the preservative already in, then no, don't rinse it. But if not, if it's a core bottle and you add the reagent in after, or the stabilizing compound, then I advocate rinsing it. I've even seen sterile bottles with a coat of dust inside. So that's what kind of has pushed me in that direction. But that's going to be laboratory and sample specific. Thank you.
When you're talking about flooding the well, like you say, open hole or no screens. One thing, if I'm going to a well, oftentimes you don't actually know what the well is, and you don't. My thought is I don't want it to collapse. The pump, so it's like if the pump is set 50 foot in a 100-foot well, you don't really want to get down there and mess up the walls, have it cave in, ruin it. But yet, more or less, you're saying in order to do a good job, you got to get down there.
Yeah. What's the doctor's code? Do no harm. And especially on older well systems where there may be no history at all,
Yeah,
whether
exactly.
within the government or with the owner.
What do you mean like that?
Yeah, and so you got to do a lot of discussions with them and say, hey, if I'm going to do this right, this is the way I need to do it. And maybe it's
no risk, no reward.
Right. But if we've done that testing, and we know that there's a bigger issue down there, then we've got to be a little more aggressive. But if it's a low count and we don't have any of these other indicators, then we can go in with a little softer touch, and then just kind of ease in that solution, try and disperse it as best as possible. It's a challenge, and I don't mean to make light of
Most
it.
people, most wells in my area, for instance, the residential, they're not deep, and people don't really see chlorination as that high tech,
Mhm.
you know, and they figured, they call up the health department, they say double jug it in bleach in it, and that's gonna fix you up.
Yeah.
Well, it doesn't. And so every step is more invasive, but, you know, you do it to an old well, like I say, you hate to ruin it, but you might. And, so yeah, just one thing.
And, you know, like the extension offices and sanitariums in my area that are, 1,000 parts per million, shock the well. And, you know, and so we're back to education, and I wish they were here today too. You know, because they've got to be part of the solution.
Well, that's the first time I heard that, because I've been shocking,
You've been-
You know, yeah.
Not a little good.
Any other questions or comments? Okay.
Excellent presentations, thank
Very
you.
good.
Thank you. Am a lot ahead of schedule. John?
Yeah, I'm just gonna let them know, there is, we do have some brochures, if anybody is interested.